Thermal energy can be generated due to conversion from some other energy form. This can include conversion from electrical to thermal energy, from electromagnetic to thermal energy, and exothermic, just to name a few. Generation occurs within the medium, so we consider it a volumetric rate. So in this screencast, we'll look at the temperature distribution for one-dimensional steady-state conduction with uniform generation. So let's start with a plane wall. So we have a plane wall that has a length of 2L. So basically, we're going this way. We're going to call this the midplane. And so this is minus L and L. So we start with the appropriate form of the heat equation. So that's d squared T dx squared. Again, it's in the x direction, plus Q dot, and that's our thermal energy generation term, divided by K, which is our thermal conductivity, and this equals 0. So again, this Q dot is equal to our generation term divided by the volume. So when we integrate this, we end up with the temperature distribution. So the first integration gives us dt dx plus Q dot over K times X equals our first constant. And then our second integration leaves us with T of X equaling minus Q dot over 2K times X squared plus C1 times X plus C2. So in order to solve for our constants, we're going to have two boundary conditions. The simplest is if we know the surface temperature of each wall and its constant. So for example, we can say at x equals L, T equals TS1. And then we can say at x equals minus L, T is equal to TS2. And if we use these boundary conditions, we end up with the first constant, C1, is just TS2 minus TS1 divided by 2L. Our C2, a little bit more complicated, is that Q dot term divided by 2K, all times L squared, plus TS1 plus TS2 divided by 2. And so when we put this all together and cancel out terms, etc., simplify, we have that our T of X is equal to our Q dot L squared over 2K. And keep in mind, remember that this is a length of 2L, so that L is half of the plane wall. And this is 1 minus x squared over L squared plus TS2 minus TS1 divided by 2. And this is multiplied by x over L. And finally, we add to that TS1 plus TS2 divided by 2. Note what happens, though, when we use Fourier's law. So we find that when we solve for the heat flux, which is equal to minus K dt dx, we end up with minus K times Q dot L squared divided by 2k, and this whole thing is multiplied by minus 2x over L squared, plus TS2 minus TS1 divided by 2L. And this is equal to, simplifying it further, Q dot times X minus K TS2 minus TS1 over 2L. And I got this by just taking this temperature distribution that I have up here and taking the derivative of it with respect to X. What's interesting about this is that here the heat flux is a function of X, unlike one-dimensional steady-state conduction without generation, where the heat flux is independent of X. Now we're going to look at symmetrical boundary conditions. In other words, TS1 equals TS2, and we're going to just call that TS. So again, if we go back and look at our wall here, what that means is we have a temperature here, a temperature here, they're the same, and it is symmetrical. So that means that our new temperature distribution is a little simpler. T of X equals, again, Q dot L squared over 2K times 1 minus X squared over L squared plus our surface temperature. Because of the symmetry, we can treat the surface in the middle as adiabatic. We can find our maximum temperature, which is going to be at X equals 0, and that's going to be Q dot L squared over 2K plus the surface temperature. And that allows us to find the surface temperature, T0 minus Q dot L squared over 2K. Now our temperature distribution becomes T of X is equal to Q dot L squared divided by 2K times 1 minus X squared over L squared plus T0 minus Q L squared over 2K. And so what this again simplifies it to is that T of X minus T0 equals Q dot L squared over 2K times minus X squared over L squared. So note we don't have to know the surface temperature to find, as long as we know the centerline temperature, to find a temperature at any X within the plane wall. So finally, we're going to do TS minus T0, subtracting the two above, and then give a dimensionless temperature, Tx minus T0 divided by Ts minus T0, and that's just equal to X over L squared. So in order to use the above results, we need to find T sub S. And one of the most common situations is that convection equals conduction at the surface if we neglect radiation. So minus K dt dx at X equals L equals H Ts minus T infinity, or the temperature of the bulk. So referring to our temperature distribution from above, this term is just equal to Q dot L, and that's going to equal H Ts minus T infinity, or our surface temperature is equal to our generation term, Q dot, times the length divided by our convective heat transfer coefficient plus T infinity. Another thing we can do, and it's a lot easier, is you can do an energy balance around the plane wall. So this is that the generation rate has to equal the rate of energy out. And this is going to be per unit area. So that's Q dot, remember that's a volumetric term, times L is going to equal H Ts minus T infinity. And remember, this is per unit area. One of the things you have to be careful of with this approach is to watch your units. So solutions using other boundary conditions, as well as solutions for spherical and cylindrical walls with uniform generation, can be found in appropriate tables.